Okay, so we're going to now talk about the domain of polynomial functions and rational functions. And in this lesson, that's all we're going to look at are just polynomial and rational functions. Now, for the next 2 weeks or so, 3 weeks, you're going to be focusing on mainly polynomial and rational functions. So first of all, let's look at examples of polynomial functions, what makes those polynomial functions, and how to find the domain of polynomial functions. All right, so these are going to be examples of polynomial functions. All right, so here's some examples of polynomial functions. F of x equal 2x squared minus 5x plus 1. So that's an example of a polynomial function. Now, first of all, what makes this a polynomial function is for one thing, look at the exponent. So if you look at the exponent of the variable, that's a positive integer. If you look at the next variable, the exponent is a positive integer. It's a positive 1. Okay. Now, notice that the denominators, if you were to write this as a fraction, the denominators are 1. So 2x squared over 1, negative 5x over 1 over 1. Okay. So it's going to look like this. It's always going to look like this form. So when we talk about polynomial function, just keep in mind that it's going to have the form where you have some number times x to a integer power. So where n is greater than or equal to 0. Okay. So notice that in every term, if you look at the exponent, if you look at the exponent, the exponent is a positive integer greater than or equal to 0. So that's 2. This is 1. And notice that the constant is can be written as 1 times x to 0. So that's where that equals 0 comes from. So you can write 1 as 1 times x is 0, because remember, x to the 0, any number raised to the 0 power except 0 is 1. So x to the 0 is 1. 1 times 1 is 1. Okay? So your constant, if you write it as a variable expression, you're going to have, in this case, 1 times x to the 0. Now, I want you to also notice that this largest exponent that you see is 2, so that's a quadratic function. A quadratic function. All right, a quadratic function. Another example of a polynomial function would be something like this. G of x equals 2x plus 5. So again, notice that each term in this function has this form. So you have 2x to the first, so the exponent is a positive integer or 0. And your constant 5, you can write 5 as 5 times x to the 0. So, so notice that your exponent, it can be 0, 1, 2, 3, 4, and so on. So 0 or any positive integer. All right. Now keep in mind from previous lessons that you know that this is a linear function. This is a linear function. All right, another example would be something like h of x equal negative 3x cubed minus 5x squared plus 6x plus 2. All right, so that's another example of a polynomial function. And again, what makes it a polynomial function is that if you look at the exponent of the variables, so 3 is a positive integer, 2 is a positive integer, x to the first, so 1's a positive integer, and 2, remember I can write 2 as 2 times x to the 0 power. So that exponent is 0. Okay? Now since the largest exponent that you see is 3, that's called a cubic function. It has a special name, a cubic function. Now, not all polynomial functions have a name. We just call a few of them with special names. So, quadratic function occurs quite often in your courses. Linear functions occur quite often. Cubic functions occur often. All right, and let's look at another one. So, k of x equal 2 fifths x to the fourth plus 7x cubed plus 2x minus 5. So again, that's a polynomial function. This is a positive integer. 4 is a positive integer. 3 is a positive integer, x to the first, so 1's a positive integer, and your constant. Okay? Now, the largest exponent is 4, so it has a name also, and we're going to call that quartic function. And so for the first, for these, there are special names. For the others, um, we just call it a polynomial function. Okay, so let's look at this one. So h of x equal 7x to the 6 minus 7x cubed plus 4x squared. So again, that's a polynomial function. Okay, now what are uh, what are examples of of functions that are not polynomial functions? So let's look at a couple examples. So not polynomial functions, not polynomial functions. Okay, so an example would be something like um, h of x equal 2x to the fourth minus 7x cubed plus 3x to the negative second plus 5. All right. Now, what makes this a function that it's not a polynomial function is this exponent right here. So remember, in order for it to be a polynomial function, the exponent of the variables must be a positive integer or 0. Notice this is negative. So since that is negative, this is not a polynomial function. And the same thing for this. I could have f of x equal 3 x to the 7th power plus 2x to the 3/5 plus 7, let's say. So it makes this not a polynomial function is the fact that this is not a positive integer, right? Okay, so it's a rational number that's not an integer, 3/5. Okay, and then another one would be something like this. So let's suppose we had k of x equal x plus 5 divided by x minus 3. Now, notice that in these polynomial functions, when we first talked about this, I said that if you look at the denominators, all these terms are being divided by 1. 2x squared divided by 1, negative 5x divided by 1 divided by 1, 2x divided by 1, 5 divided by 1, and so on. Okay? If you look at this, though, this denominator, so you have this fraction, this denominator has a variable expression. Now, whenever you have a fraction and the denominator contains a variable, then we're going to call this a rational function. A rational function. So that's not a polynomial function, that's a rational function. The fact that the variable occurs in the denominator makes this a rational function. Okay? And that's one of the ones that we're going to talk about today. Okay, now let's look at this idea. Okay, so let's go ahead and discuss how to recognize the graph of a polynomial function. So the graph of a polynomial function is going to be a smooth curve. A smooth curve. All right. And you're going to notice there are going to be arrows on the ends. Arrows on ends. All right. So in a future lesson, we're going to talk about the word end behavior. So end behavior. So on the ends, you're going to see arrows. And so here's how it's going to look. So an example would be something that you had previously where you graphed a quadratic function and you ended up with a parabola. So you see this smooth curve? So that's the graph of a polynomial function. Something like this. So this is a smooth curve. Notice you have arrows on both ends. It just so happens that these arrows are pointing in the same direction. You could have something that looks like this. Okay, notice a smooth curve. That's a polynomial function. You have arrows on both ends. Now these arrows are pointing in opposite directions. You could have something like this. So you have a smooth curve. Okay, you have arrows on opposite directions. All right, so things like that. So uh, you could see situations like these, and those are graphs of polynomial functions. Okay, now let's go ahead and look at this and look at some graphs in terms of grid. Now, so so what I want to do with this information here is kind of talk about, well, what is the domain of these? So what is the domain? What is the domain of a polynomial function? So that's what we're interested in finding out. What is the domain of a polynomial function? Well, if I look at this in terms of a graph and I look at that parabola that we had earlier, okay? And remember in a previous lesson you learned how to find the domain given a graph. So if I find the domain, remember the domain is a set of x coordinates, and so we go along the x-axis. So if I look at this, and remember this arrow is going this way, this arrow is going this way, so I'm going from negative infinity to infinity. So the domain in this situation is negative infinity to infinity. So in other words, any value of x here. So if I look at this x value, there's going to be a point of the graph with a y value. If I look at an x value over here, there's going to be a point of the graph with a y value. So so every real number will be associated with a point on the graph. Okay, so that's the domain. And remember, when we talk about infinity, negative infinity, you always use parentheses. Okay, now let's look at this example. So, so what if we had, let me go ahead and quickly find this page. So what if we had this? All right, so what if we had this graph? Let's suppose we had something like this. So we have this graph that looks like this. Okay. All right, and again, notice that we want to find the domain, so we're going from left to right. So again, notice these arrows are going down and this arrow is going up. So I'm going from negative infinity to positive infinity. So the domain is negative infinity to positive infinity. So every real number in the domain is going to be associated with a point on the graph. So if this keeps going down like this, then at some x value here, there's going to be a point on the graph. Same thing here. Way on this side, there's going to be a point on the graph. Okay? So that's the domain. Negative infinity to infinity. All real numbers. The domain, another word of saying this, is all real numbers. Okay? All real numbers. Okay? Now what about if we had this graph? So let's say we had something like this. Okay? So that's a graph of polynomial function. You have a smooth curve. But again, notice these are arrows on both sides. Notice that the domain, remember the domain set of x coordinates, so you go from left to right. So as I go from left to right, I'm going from negative infinity to positive infinity. So the domain, negative infinity to positive infinity. Okay? Now, one thing I got to mention is that if you look at the graph of a line, okay, graph of a line, now, that is still a polynomial function. So even though it doesn't look like a smooth curve, by definition, when you look at the function that we had earlier, let's see this one. So remember this right here. So that's a linear function. So that's a polynomial. So the graph of a linear function. So a linear function is a polynomial function. And remember the graph looks like this. So even though you don't think of this as being a smooth curve like this, it is still a polynomial function. You can think of it being smooth as this idea that you're just going from left to right, right? That's a smooth transition. It's not curvy, but it's still smooth, right? Okay, so the domain, again, is negative infinity to infinity. As you go from left to right, every real number on this x-axis is going to be associated with a point on the graph. All right, so that brings us to this idea then. What is a domain of a polynomial function? So, considering all the examples we just talked about, the domain of a polynomial function then needs to be all real numbers. So the domain of a polynomial function is all real numbers. So negative infinity to infinity. So that's interval notation. So remember, this is interval notation. And you're going to be told to write this in interval notation. So always go from smallest to largest. So negative infinity to infinity. And remember, when you talk about infinity and negative infinity, you always use parentheses. But remember, we are talking when you state the domain is from negative infinity to infinity, that means all real numbers. Okay? All right. Now, let's look at some examples. Okay, so the direction is going to say something like this. Okay, so determine the domain of each function, and they're going to write the domain in interval notation. Okay, number one. F of x is equal to 5x plus 1. All right, so you have to recognize that this is a polynomial function. Okay, now for almost all of you, you also know that this is a linear function, and when you graph a linear function, you have a line. And in this case, the slope would be 5, right? So it would be increasing. But basically, you recognize that this is a polynomial function. So this is a polynomial function. And we just saw that the domain of a polynomial function is all real numbers. Negative infinity to infinity. Okay? Number two, g of x equals 2x squared minus 3x plus 1. Again, all of you know that this is quadratic, and the graph of a quadratic function is a parabola. In this case, it's going to open up, but notice that the domain here is from negative infinity to infinity, all real numbers. But again, you didn't have to recognize it as quadratic, although you do know that. You just have to also know that this is a polynomial function, and the domain of all polynomial functions is all real numbers. But as an interval, you're going to say negative infinity to infinity. Number three. All right, now let's suppose we had this for number three. We had h of x equal 7 divided by x plus 2. Okay, so again, notice from a discussion we had earlier that a fraction where you have a variable in the denominator, we have a variable expression in the denominator, is not a polynomial function. It's a rational function. So you have to recognize, hey, this is a rational function. That's a rational function. And you have to remember this now. A rational function you cannot divide by 0. Never divide by 0. Okay? Never divide by 0. So for example, 7 divided by 0 is undefined. So when you're talking about a rational function and you want to find the domain, you first of all need to determine what the restrictions are. So you have to find the restrictions. You have to find the restrictions. And when I say restrictions, I mean the restrictions on the domain. So if I determine the restrictions here, I got to find out what makes this denominator equal to 0. So you're asking yourself, where is x plus 2 equal to 0? And all you do is solve for x. So when you subtract 2 from both sides, you get x to be negative 2. And you found the restriction. So this right here is the restriction. So which means that my domain So I can use any number for x except negative 2. Because if I use negative 2, negative 2 plus 2 is 0, and 7 divided by 0 is undefined. So the domain is all real numbers, except negative 2. Okay, but remember, they want you to write the answer in interval notation. So here's what you got to do now. So what I would do is I would write a number line like this, and then I would put negative 2 on it, and then I would cross it out. I'm crossing it out because I cannot use it in my domain. But notice what this negative 2, when you cross it out, notice that little cross out symbol divides this number line into two intervals, right? Two intervals. So, and remember, you always go from left to right. So as I go from left to right, notice I'm going from negative infinity all the way to negative 2, right? And then you're going from negative 2 all the way to infinity. So as an interval, now here's how you're going to write this as an interval. So you're going to say answer. The domain as an interval will be parentheses, negative infinity, comma, negative 2, parentheses, close parentheses, union, and then open parentheses, negative 2 to infinity. So this right here represents these two intervals. So you're going from negative infinity to negative 2, and then you're going from negative 2 to positive infinity. Notice the parentheses. You use parentheses with negative 2 because you cannot use negative 2 in the domain. Negative 2 is not in the domain. If you put a bracket, then you're indicating that negative 2 is in the domain, which you know it cannot be because it makes the denominator 0. All right, so that's how you do this. It helps to draw this right here. Okay, so that's the answer to number 3. Okay, let's look at number 4. So in number 4, let's suppose we had this for number 4. Let me go ahead and do number 4 here. So this number 4. We have k of x equal 4x to the 5th minus 7x to the 4th plus 2x cubed minus 7. All right, so again, notice this is a polynomial function. Polynomial function. And the domain of a polynomial function is all real numbers. As an interval, you go from negative infinity to infinity. So if you look at this on the number line, there's no restrictions, so nothing is crossed out. So you go from negative infinity to infinity. Okay, but you got to put it as an interval. Okay, number 5. All right, number 5, let's suppose we had this for number 5. All right, number 5. We have f of x equal x plus 7 divided by 2x minus 3. Okay, so now again, notice that this is a rational function. Okay, rational function, and you have to remember this about a rational function. You cannot divide by 0. So we got to find the restrictions. So we have to find the restrictions. Find restrictions, if any. Okay, so find the restrictions. So you're asking yourself, where is 2x minus 3 equal to 0? Where is 2x minus 3 equal to 0? So it doesn't matter what the numerator is. The numerator can be 0. It is the denominator that cannot be 0, because you can never divide by 0. So if I want to find out what I cannot use as the domain, what I have to restrict, I have to find out what makes the denominator 0. And so you're just solving this equation. So this is a linear equation. You're going to add 3 to both sides. So you get 2x equal 3, and so x is 3 halves. So that's your restriction. So you can't have 3 halves in the domain. So basically, your domain in words, the domain in words is all real numbers except 3 halves. But remember, you want to write this as an interval. So think of this on the number line, put 3 halves in the number line, and then cross it out. So when I cross it out, I have two intervals. So you go from negative infinity to 3 halves. Remember, we always go from left to right. And then you're going from 3 halves to infinity. But remember, two intervals. So here's your answer. Negative infinity to 3 halves, all parentheses, union, and then 3 halves to infinity. So what you've written is that the domain is all real numbers except the 3 halves. Okay? All right, number 6. And number 6, let's suppose we had h of x equal x plus 1 divided by x squared minus 25. Okay, so again, notice this is a rational function. So since this is a rational function, I have to remind myself that I've got to determine the restrictions. So I got to find those restrictions. So to find those restrictions on the domain, I need to look at the denominator. It doesn't matter what the numerator is. It's the denominator that cannot be 0. So I take that denominator and I set it equal to 0. Now notice that in the previous problem, when I set the denominator equal to 0, this was a linear equation. Here, when I set the denominator equal to 0, this is a quadratic equation. And I can solve this by factoring. This is the difference of two squares. So I'm going to go ahead and factor this. So that's x plus 5, x minus 5. And then using a zero factor property, I set each of those equal to 0. And I find the restrictions to be a negative 5 and a positive 5. Okay? And you can see that works because if you substitute 5 into x, notice the denominator. 5 times itself is 25. 25 minus 25 is 0. So you're dividing by 0. Same thing for negative 5. Negative 5 times itself is a positive 25. 25 minus 25 is 0. So those are restrictions. But notice this time you have two of them. You have two restrictions. So in words, you're saying that the domain is all real numbers except negative 5 and 5. But you got to write this as an interval. So you can put this in the number line and make sure in the number line you put these numbers in correct order. So negative 5 is going to be on the left, positive 5 is going to be on the right. Cross those out because it's not part of the domain. But notice this time that you have three intervals. Three intervals. Okay, so those two restrictions divide the number line into three intervals. So you go from negative infinity to negative 5, negative 5 to positive 5, and then positive 5 to infinity. And so your answer, you're going to say negative infinity to negative 5, union negative 5 to positive 5, union positive 5 to infinity. And that's all it is. Okay, that's all you do. Okay, let's look at number 7. Okay, so number 7, let's suppose we had this for number 7. For number 7. Okay, we have f of x is equal to 6 divided by x squared plus 9. 6 divided by x squared plus 9. Notice you need to determine what kind of function this is. So this, since the variable occurs in the denominator, this is going to be a rational function. And then I got to find the restrictions. So we have to determine what's going to make the denominator 0. So where is x squared plus 9 equal to 0? Okay? And so first of all, notice that this is a quadratic equation. Secondly, notice that this is the sum of two squares. And so remember that the sum of two squares cannot be factored, right? And you may say, well, I don't know how to factor this. Well, first of all, it cannot be factored. But even if you brought the 9 over, so you could say, well, I'm going to bring the 9 over, and so you get x squared equal negative 9, right? But notice see this side's negative. So no matter what number I square, if x is positive and I square it, it's going to be a positive number. A positive number is never equal to a negative number. If x is negative and I square it, like let's say negative 3, right? So you're probably thinking negative 3. Well, negative 3 times negative 3 is a positive 9, and that's not equal to negative 9. All right, and so you'll notice that, hey, so there's no solution here. So I cannot solve, so there's no real number, that will make x squared plus 9 equal to 0. And so and some of you may say, and I've seen this before, some of you may say, well, I factored it as x plus 3 times x plus 3. No, you didn't. That is not this, because if you FOIL it out, you get x squared, the outer's 3x, the inner's 3x, that's 6x, and then plus 9. 3 times 3 is 9. But notice you have that middle term, that x term, and this did not. So that's not the case here. So this right here, there's no real number that will make this denominator equal to 0. So what that means is this: there are no restrictions. So this has no restrictions. So this function has no restrictions. So that means that if you look at the number line, there's nothing to cross out on the number line. So you're going from negative infinity to infinity. So that's the domain for this function. So the answer is going to be negative infinity to infinity. Okay, number 8, we have m of x is equal to 2x minus 1 divided by 2x squared plus 7x plus 3. So this is a rational function. I have a fraction with variables in the denominator, so that makes that a rational function. So I got to find the restrictions. So I have to determine what values of x must I exclude from the domain. So we got to find out where is the denominator equal to 0. So we have this quadratic equation, so let's go ahead and factor this. So this can be factored. And so I get 2x, x, this is going to be 3, 1, and both positive. And then setting each factor equal to 0, I get x here to be a negative 1/2, and I get x here to be a negative 3. So those are your restrictions. So these two values of x will make this denominator 0, which in turn makes this function undefined. So those are the two numbers. I cannot use. So what this these restriction tells us is that the domain is all real numbers except negative 1/2 and negative 3. But you need to put this in interval notation. So on the number line, put them in correct order. So negative 3 is going to go first, negative 1/2 is next on the right. Cross them out, and notice you have your 3 intervals. So I'm going from negative infinity to negative 3. So the answer, negative infinity to negative 3. Notice parentheses. In all the problems we've done in this part, all of the they've all been parentheses. None of them were brackets. So negative infinity to negative 3, union negative 3 to negative 1/2, union negative 1/2 to infinity. Okay? All right, let's look at one more, and this is going to be number 9. Okay, number 9. All right, finally, let's suppose we had this. We had k of x is equal to 2x plus 5 divided by 4x. All right, and then again, this is a rational function. So I've got to find the restrictions. And remember, some rational functions don't have restrictions. We saw that, right? So we saw that here, that there was no restriction. So the domain is going to be all real numbers. All right, so let's find the restrictions. So in this case, I look at the denominator and I ask myself, where is this denominator equal to 0? Well, this is a linear equation, and so if I divide both sides by 4, I get x to equal 0. So there's your restriction right there. So that's my restriction. Again, remember that x equals 0 means that the domain is all real numbers except 0, because 0 makes the denominator 0. So look at the numerator. So when x is 0, 2 times 0 is 0, 0 plus 5 is 5. So the numerator is 5. Again, it did not matter what the numerator was to begin with. It's the denominator. 4 times 0 is 0. So 5 divided by 0 is undefined. Okay? So put that in the number line. 0 in the number line, cross it out, and then you have two intervals. So you're going from negative infinity to 0, and then from 0 to infinity. So there's your answer. So you're going to say negative infinity to 0, union 0 to infinity. And so that is the part of this week that's dealing with the domain of polynomial and rational functions.